probably had to go to ring ceremony practice. So anyway, make sure you take all these notes. And we're going to go all the way from number 1 through 21. And then all the rest of them will be on a different video. The first thing I want you to do is draw a transverse wave. So this is very much similar to the slinky that we used. And this is also found on page 492 of your hymn book. So make sure that you look at page, I don't know why it's 2, but 492 of your books, and you'll see this exact same picture to write down. And this is also probably going to be the first question on the test. So the height of the wave is, at the very, very top of the wave, we call that a crest. The bottom of the wave is called a trough. And the amplitude, you got to be a little bit careful because it's not from the top crest to the bottom of the trough. It's actually from the top of the crest to the midpoint or the resting point of the wave. Now, the next thing I do is the distance from the crest of one wave to the crest of the next wave, and we call that a wavelength. Now we already used W for weight and W for work, and since this is circular motion, we're going to use the Greek letters like we did before, and so we're going to use the Greek letter lambda, which is like an upside down Y. So that upside down Y you see there, it's called lambda, and it means wavelength. Now the big deal about a transverse wave is it's much like a slinky. The slinky goes up and down, but the energy goes from left to right. And but on the next wave, which is more like a sound wave, it's called a longitudinal wave. Now in a longitudinal wave, the energy and the mass, or the energy and the matter, both move the same direction. So think about a slinky being stretched out, but it's going back and forth from left to right. And I drew a pathetic drawing of it, but there's a much better picture in your hymn books on page 515. If you're dyslexic, that's page 515. If you're vertically dyslexic, that's page SIS. And so when you hold the spring here, thank you so much for holding this for me, Isaac. When I stretch out the spring, I'm going to scrunch up one section of the spring called a compression. That's the part that you see in the middle of your screen there. And the other part of the spring is stretched out. And now the spring bounces back and forth from left to right like this. Okay? Instead of going up and down, it's going back and forth from left to right. And you see the compression follow through. So once again, the energy and the spring are both going the same direction. It's a little bit different when we call the parts of the wave. The parts that are stretched out are actually called a rarefaction. We've got sort of erased here, so a rarefaction is R-A-R-E-F-A-C-T-I-O-N. Rare as in not cooked beef. Faction as in something that's a part of something. Not a fraction, but a faction. And then a compression is simply the part of the spring that's all compressed together. Okay, now 3A and 3B there. 3A asks, what is the frequency of a wave? I sort of it's a typo in there. I should say, what's the frequency of a wave? So you got one wave that passes through a certain point every 0.25 seconds. Well, the formula for frequency is the number of waves per second. So I had one wave going by every 0.25 seconds. So 1 divided by 0.25 is 4 waves per second. And we have a special unit for that. We're going to call that hertz. Because something that's an owie hurts. HZ is God's name. It's really common. So hertz is simply a wave per second, or a cycle per second. We also have 3B there. 3B says, what's the period of that wave? Well, if you remember from the chapters before, when we were doing circular motion, period is a great big T, it stands for time, but it's not waves per second, it's seconds per wave. And the problem actually gives that to you, because it says that it takes 0.25 seconds for one wave to pass, so your answer is simply 0.25 seconds. And there's no special unit for that except for seconds. On number 4, it says, what is the speed of light? So the great big new equation for this chapter is going to be that the velocity of a wave is the wavelength times the frequency. You can also make a brand new right triangle for that. Let's say that V is lambda times f. So in number 4, it says, what is the speed of light? So I'm looking for V. If its wavelength is 7.5 times 10 to the negative 7th meters, and its frequency is 4 times 10 to the 14th hertz. Well, when you put these in your calculator, don't forget it's 7.5 second button, EE button, negative 7. You don't put in the times 10. Okay? And that gives you 3 times 10 to the 8th meters per second. Now that's going to be a brand new constant. That's the speed of light constant. It never, ever changes. And so they often say the speed of light is C. I wish they wouldn't have used C, because we already use C for Celsius and specific heat. I'm trying to think what else, calories and everything else we use it for. But in this case, C stands for speed of light, and it's always going to be 3 times 10 to the 8th meters per second. 3 times 10 to the 8th. Now, number 5, it asks for you to find the wavelength. So wavelength is lambda, which means it's velocity divided by frequency. We see that the frequency of this sound wave is 220 hertz. I'm going to put that on the bottom of F is. The sound speed is 343 meters per second, which that on top of the V is. And you end up getting 1.5, and the wavelength is always measured in meters. Okay, now we're going to do number 6 here, and I actually made a picture of a oscilloscope of me doing 2 things. On this first graph here, I'm singing really, really softly into a microphone. I'm going like that. That's this one right here, so this was soft. And the next one I'm going sing the same note, just louder. If you notice, what happened to the graph? It simply got taller. So your answer to number 6 is when the amplitude goes up, it gets louder. That's number 6. Okay, I'm going to skip number 7 real quick, and I just want you to look at number 8 and 10, because we're still dealing with sound waves. On this first one right here, this is number, so this is the first one. This is actually number 8. This is going to be number 10. If you notice, the frequency is very, very, very fast in number 8. And so when I was singing number 8, I was singing this note, a real, real high pitch. So the higher the frequency, the higher the pitch. Now on the second graph over here, the one on the left, I was singing a real, real low note. I was going, oh, like that. And so if you notice, the louder the pitch, the taller the wave. So you were hearing this wavelength right here. Notice how far apart those waves are. So the bigger the wavelength, the lower the pitch. Now, if you notice in this one right here, you see a whole bunch of other little waves. That's because my voice actually produces 4 notes when I'm singing this particular note. Now, you only hear the big bass one, but if you notice, I got this one, this one, this one, and this one, okay? And so even though my voice is producing 4 notes, you only hear the big tall one. But we'll get into overtones a little bit later, especially dealing with the Bulldog Beats here, the acapella choir, how they can change their mouth shapes and change where they put the pitch. And we can actually have 2 people sing, but you're going to hear 3 different notes of overtones. So once again, higher pitch, it's when it's really, really high frequency. The big wavelength means lower pitch. Now let's look at light. Okay, this is going to be number 7, and instead of a microphone, I now hook the computer up to a light sensor. And we made the light sensor, the computer, take data once every 120th of a second. So it's taking light sensing or data 120 times a second. Well, you got to remember back when we were doing those timers, those electric timers, the electricity goes on and off 60 times a second. So sometimes you're seeing the light when it's turned on, and sometimes you're seeing the light when it's turned off. So when the amplitude gets really, really, really high, that means the light gets brighter. So that's your answer to number 7. If the amplitude goes way down, like over here, that's when it's dark or it's no light whatsoever. Now, I can't demonstrate the numbers 9 and 11 with the computer very easily, so what I'm going to do is I'm going to go ahead and just show you the Wrights Wave thing. Okay. Number 9, we get into the colors of the rainbow, Wrights Wave. So red, orange, yellow, green, blue, indigo, and violet. And if you look at this wave down here, these have very, very large wavelengths. So I have high wavelength or high lambda, but it's low frequency. There's not a lot of waves that go by very frequently. As it becomes bluer, you get very small wavelengths. So these are real small wavelengths, but it's very, very high frequency. So in number 9, if you have high frequency light, objects will appear bluer. And number 11, as you get a greater wavelength, an object will appear redder. For number 12 and 13, both the same answers. As frequency goes up, wavelength will decrease. But the wave speed always stays the same. For light, it's always going to be 3 times 10 to the 8th. On number 13, as wavelength goes up, frequency goes down. Frequency goes up, wavelength goes down. But the speed always stays the same. So 12 and 13 give you both the same answers. Now, if you notice on those, now if you've never been to a race car track, you're going to realize something called the Doppler effect. I'll show you some Doppler weather radar and stuff like that a little bit later. But we'll do a lab tomorrow where we take a person's car, have them go down Brook and Breck with the horn on. You'll hear it as it goes by. It'll go, over the race car, go, like that. Anyway, that's called the Doppler effect. As something comes at you, number 15 says the pitch will increase. So you'll hear it go, as it goes by, so number 16 says as it flies by you, it will actually decrease in pitch. Well, not only does that work with sound, but it also works with light. So anything that's coming towards you will appear bluer, and anything that's going away from you will appear redder. So when I showed you that picture last week of that great big book and we were looking at the galaxies, most of the galaxies on this page in this book appear to be yellow or orange, a little bit red shifted. So what does that tell you they're doing? That's right, they're moving away from you. And so that's the evidence that we have that the universe is actually expanding. So what I'm going to do right now with a slinky is, and it's also this little string that's going around in circles that I'm putting a strobe light on my desk, is this. I'm going to have a wave that bounces back and forth between 2 things. It's called a standing wave. But here's the issue. I'm going to have a crest go in this way, but it's going to bounce back as a trough. Well, when the trough and the crest meet right here in the middle, the crest gets pulled down by the trough gets pulled up by the crest, and you end up getting what we call a node. So this picture becomes something that looks like this. Okay? So when you're looking at it on my desk, you're going to see what we call a standing wave. And it looks like a complete figure 8 like this. It's bouncing back and forth. Okay? This is called a node, and this is the answer to number 19? No. Yeah, actually 19 is going to be Sonic Moon. I think this is the answer to number 20. What's number 20 say? Yeah, when 2 crests overlap, that's going to be called an antinode and constructive interference. Constructive. I got to spell that one more time. Constructive. There you go. constructive interference. And so this part here would be called the antinode. The part in the middle where there's no movement whatsoever, node movement right here, is the answer to number 21, I think, for the node. And that's where you have destructive interference because the crest and the trough destroy each other. And in our next chapter with sound, you'll hear no sound at a node, you'll hear really loud sound at an antinode. Let's go to number 19, and let's simply show you a video of a sonic boom, and that's the answer to number 19. And that's when the jet's sound waves all build up on top of each other. So let's see if I can give you a great example. All right, one last thing here is if you look down here in the lower left-hand corner, you're going to see a jet that's making sound waves, and I can't show it to you actually moving because it's a simulation. But if you notice right here, the frequency of the waves is very, very high frequency when it's coming towards you. Now I'm sitting here down here like this. Okay? So this is me. And then behind the jet, though, is very, very low frequency waves. And so that's why you're going to hear this big as the jet actually goes by. Okay? So therefore, we have a change in pitch called the Doppler effect. Now on the right-hand side, this is where we get number 19, the sonic boom. You like Sky High, that great movie. Anyway, sonic booms are caused by jets that are going the speed of sound, and they make their sound waves on top of each sound wave over and over and over again. You get this constructive interference that we talked about, where you get these great big super crests or antinodes. Well, if I'm right down here, I don't hear anything until all the waves hit me all at one time, and that's why you hear this great big boom, and that's what we call a sonic boom when something goes the speed of light, or speed of sound, rather. So anyway, hope you enjoyed the show, and hope everybody watches this and didn't get a chance to see the notes. Love you. Bye. Show you.